Hi everybody, Mrs. Pesic here,
And Miss Bella here.
and we're looking at section 3.6, Fundamental Theorem of Algebra. Your objectives in this section are to use the fundamental theorem of algebra and its corollary to write a polynomial equation of least degree with given roots. And another objective is to identify all of the roots of a polynomial equation.
Okay, so far we've learned about several important properties about real roots of polynomial equations, and they all kind of relate to the same thing, but they're just presented in different ways. So let's just do an example here to talk about what this would look like. So let's say, for example, we had a function f of x is equal to x squared minus 9. Okay, so if we were asked to solve that, well, we know from factoring that we would factor that to x squared minus 9 equals 0 to start off, and then two sets of parentheses, x plus 3 and x minus 3, because it was a difference of perfect squares. So this would tell us for this first statement, if I wanted to, well, first, okay, let's solve first. So we'll say x plus 3 equals 0, so our two answers, x equals negative 3 and x equals positive 3. Okay, so the first statement here says that a real number r is a root of the polynomial equation p of x equals 0. That means in our example that 3 is a root of our function, x squared minus 9. And we also could say that negative 3 is a root, because we have two answers there. Our second statement that p of r equals 0 means if we take our function and we plug in 3, and we say 3 squared minus 9, that should equal 0. And also, if we did that with negative 3, same thing should happen. Our third step, or our third explanation here, r is an x-intercept of the graph p of x, which means if we were to graph our function x squared minus 9 on our calculator, or did it by hand, we would see that it crosses the x-axis at both positive 3 and negative 3. We know that that's a parabola. We know that it opens up. So again, those are the two x-intercepts. The fourth statement, well, let's clarify that for a second. 3 is an x-intercept, or again, negative 3 is an x-intercept. The fourth statement here, x minus r is a factor of p of x. That just tells us in factored form that the parenthesis quantity x minus 3 is a factor of x squared minus 9, or also x plus 3 is a factor of that, of our function we're using. All right, the fifth statement, when you divide the rule for p of x by x minus r, the remainder is 0. Again, rule is just a fancy way to say the equation. What is it actually equal to? So if I were to take x squared minus 9, that quantity, and I would divide it by one of my factors, x minus 3, well, you know, we can either do long or synthetic division there, but our remainder in each of them should be 0. All right, and our last one, r is a 0 of p of x, which means that if we were to talk about our two numbers in this case, we would say that 3 is a 0, which again is 0 means x-intercept. So 3 is a 0 of p of x, or in this case, our function is called f of x. All right, so those are 6 different things that all kind of mean the same thing. They're all equivalent, but they're just kind of presented in different forms depending on how you solve it.
Okay, so we can use this information to write polynomial functions when given the zeros. So let's take a look at an example of this. If we want to write the simplest polynomial with roots -1, 2/3, and 4, we would start by writing the factors. So if -1 is a root, that means that x plus 1 is going to be a factor. And if 2/3 is a root, then x minus 2/3 is going to be a factor. And if 4 is a root, then x minus 4 is going to be a factor. So let's start off by multiplying these two together first. So if we use FOIL on that, we're going to get x squared, we're going to get a plus 1x, we're going to get a minus 4x, and a minus 4. So that's going to turn out to be x squared minus 3x minus 4. And then we're going to multiply that by x minus 2/3. And when we do that, I probably would use maybe the box method for this. I don't think I need that many rows and columns for this box. Let's try this again. If I'm going to use the box method for this, I would like an x here and a negative 2/3 here. And I'll take an x squared and a minus 3x and a minus 4. So it looks like we're going to have x cubed minus 3x squared minus 4x, filling up our top row, and a negative 2/3 x, and thank you, negative 2/3 x squared, and this one's going to be a positive 2x, and then the last one is going to be an 8/3. All right, so our final answer for the polynomial, I'll call it f of x, would be x cubed. I can combine my like terms here, and negative 3x squared and a negative 2/3 x squared is negative 9, negative 11, negative 11/3 x squared. And then if I combine these two here, I would get a minus 2x, and then I would have an 8/3 there to finish up that function.
Okay, let's try another example with this. Again, we're going to write the simplest polynomial function with the given zeros. And if we take a look at this, again, we know that our 0 is negative 2, so x equals negative 2, which means in factored form we have x plus 2. For our next 0, we have x equals positive 2, so in factored form that it's x minus 2. And then finally we have x is equal to 4 as a 0, so x minus 4 as its factor. So in order to multiply, I'm going to multiply the first two together, and then I'll multiply it by the third. So the first two, if I FOIL those, I'll have x squared minus 2x plus 2x minus 4. Well, if I combine like terms here, I notice that I have a plus 2x and a minus 2x. So these two middle terms, those are going to reduce out and cancel. So I'll be left with x squared minus 4. So that's the first two multiply, that's product. And if I bring down my resulting term, again, you could use the box method for this one. I'm still just going to FOIL here. So first times first will be x cubed, outside times outside, minus 4x squared, inner times inner, minus 4x, and last times last will give me a positive 16. In this case, all my like terms are already combined, so I would say that my simplest polynomial function with these zeros is x cubed minus 4x squared minus 4x plus 16.
Okay, let's do one more of these. This one, we're writing the simplest polynomial function with the given zeros. If 0 is a 0, that means the factor must be x minus 0, or you could just write x for that. If 2/3 is a 0, then x minus 2/3 is a factor. And if 3 is a 0, then x minus 3 is a factor. So if I multiply x times x minus 2/3 times x minus 3, and I start here by just distributing the x, I'll get x squared minus 2/3 x. And then I want to multiply that by x minus 3. So if I use FOIL on that, I'll get x to the third. As my first terms, the outer term is going to be a minus 3x squared. My inner terms is a negative 2/3 x squared. And my last term is going to be a positive 2x. So when we combine these like terms here, we should end up with x cubed minus 11/3 x squared plus 2x.
Now, if you notice, for the degree of our function in example 1, so those are the three we just did, they always ended up being the same as the number of zeros. So again, just a quick look at that really quick to kind of look at this comparison. So in example 1, I had 3 zeros, and my highest power here ended up with x to the third. And I think all three examples we did were just like that. I had 3 zeros, I had x to the third. I had 3 zeros, I had x to the third. So if I had 4 zeros, I'd have an x to the fourth, 2 zeros, an x squared, for example. So again, this will be true for all polynomial functions. However, not all of our zeros will be real zeros. We know from section 2.6 sometimes we can have imaginary zeros. So polynomial functions, which is an example of quadratic functions, they could have complex zeros that are not real numbers. So we do have a fundamental theorem of algebra that kind of talks about this. And it says that every polynomial function of degree n greater than or equal to 1 has at least one zero. Again, a zero is the same as an x-intercept or a root. And this zero may be a complex number, which means that it might be an imaginary number. So you might not actually see it cross the x-axis at that point. And kind of more importantly, the one we're going to use more about this is what's called the corollary. So it comes from the theorem, and it says that every polynomial function of degree n greater than or equal to 1 has exactly n zeros, including multiplicities, which just means that the answers could repeat. So you could get two answers of x equals 3, but you would count that twice.
So if you had a degree 4 polynomial function, there's going to be 4 zeros. Some of them might have been repeated, some of them might be imaginary, but there's going to be 4 altogether. If you had a degree 5, you'd have 5 zeros, where some might be repeated, some might be real, some might be imaginary, but there will be 5 altogether. Okay, so to find all roots of a polynomial equation, you can use a combination of the rational root theorem, the irrational root theorem, and methods for finding complex roots, such as the quadratic formula. So let's take a look at this example. This one says solve x to the fourth minus 3x cubed plus 5x squared minus 27x minus 36 equals 0 by finding all of the roots. So in this case, this polynomial is, notice it is degree 4, and that means we are going to be looking for 4 roots. There should be exactly 4 roots. Some might be real, some might be imaginary, some might be repeated, but there will be 4. So what are the steps for doing this? Well, the first step is to use the rational root theorem to identify all of the, I really shouldn't just say rational roots, but all of the possible rational roots. So in this case, to find the possible rational roots, and you learned this in a previous section, so p over q values, the p values are going to be all the factors of your constant term, so that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6. What else goes in? Plus or minus 9, 12, 18, and 36. The possible q values, our possible denominators, are going to be all of the factors of our leading coefficient. Well, our leading coefficient is 1, so we got off easy here, and we just have a denominator of 1. That means that when we look for a possible rational root, it's got to come from this list. So if we think it looks like it's crossing through the x-axis at, at 3.5, well, that cannot possibly be the correct rational root because it has to come from this list if there's going to be a rational 0. Okay, so we're going to now test. Oh, I'm sorry. Step 2, we're going to graph this to find which of these possible rational roots might work. So we're going to type this up. This is x to the fourth minus 3x cubed plus 5x squared. I hope you're doing this with us. And then minus 27x minus 36. When we look at this, it looks to me like it's crossing through at -1 and possibly at 4, So both of those were potential rational zeros. So let's test those back on our graph. Is that going to be the next step? Next page. So we're going to test that. So let's test -1, for example. So if I do this, I get 1, -3, 5, -27, -36. So we're doing synthetic division here. I'm going to bring down my first number as a 1. I'm multiplying. I'm adding here. I get a -4. I multiply the -1 and the -4, and I get +4. I add, I get 9. I multiply, I get -9. I add, I get -36. But multiplying that by a -1, I get a +36. And sure enough, we do get a 0. That means that -1 is a 0 of the function, and that also means that x plus 1 is going to be a factor. As we said at the beginning of this video, you've got to be able to be comfortable going from zeros of a function to factors to roots of an equation and so on. So that means that if I wanted to write my equation, and my original equation was x to the fourth minus 3x squared plus 3x cubed plus 5x squared minus 27x minus 36, that now could be rewritten in factored form by using x plus 1. And then these numbers right here are going to be the coefficients of the next factor. So that would be x to the third let's do this. This is x to the 0, x to the first, x to the second, x to the third. So that's going to be x to the third minus 4x squared plus 9x minus 36. Now that's not bad, and if we wanted to find the zeros, we would, we could set this equal to 0 and this huge thing equal to 0, but this is going to be too hard to set equal to 0 right now. So instead, we're going to use synthetic division. Whoops. We're going to use synthetic, where am I at? Come back, page. Where did you go? Okay, so we're going to use synthetic division again, and we thought that the other possible 0 was 4, so I'm going to put 4 in the box, but I'm not going to go back to use these original coefficients from our first equation. Instead, we're going to use these coefficients on this factor. So I'm going to use 1, -4, 9, and -36, and hopefully we're going to end up with another 0 for a remainder. I bring down the 1, I multiply, I get 4, I add, I get 0, multiply, I get 0, add, I get 9, multiply, I get 36, and when I add, I do get 0 again, which means now I can write my equation as x plus 1, that's this x plus 1 right here, and this thing in factored form could be written x minus 4, because 4 showed up, it was a root because we got a 0 as a remainder, and then the coefficients here would be, this is x to the 0, x to the first, x to the second, that would be 1x squared plus 0x plus 9. So that looks like how we would finish this up, and I'm just going to get this x squared plus 9. So now, if we want to know when is this equal to 0, again, we set each of these equal to 0. Well, we already know about these first two. This one is going to give us -1 as a 0 of the function. This one's going to give us a +4 as a 0. But this one we haven't solved yet. So let's solve that. X squared plus 9 equals 0. Subtract 9 from both sides. We get x squared equaling -9. And we take the square root of both sides. Don't forget the plus or minus. And we get x equaling plus or minus square root of -9, which you know is the same as square root of -1 times square root of +9. So x equals plus or minus 3i. So if we were going to list all of our zeros for this, was it asking for solutions or zeros in this problem?
It just said solve. Find the roots.
Oh, it just said solve. All right, so if we were going to list all of our roots for this equation, our roots, so roots would be the solutions to an equation. Zeros would be the numbers that make a function equal to 0. So the roots for this equation, there should be 4 of them, and they are all the ones that we've listed so far. So -1, +4, 3i, and -3i. And again, remember, this came from a degree 4 polynomial equation, so there has to be 4 roots.
Okay, and I think these steps, that just was the last step from the one before that we took the quadratic and solved it. Okay, we're going to do one more like this just to practice because there is a lot of stuff that goes into this one. So the first step we're going to do is, before we can decide what we need to solve, we do know that from the start we are looking for 4 roots altogether, whether they're real or imaginary. So we're going to start off by doing our possible rational roots. That's my step 1, to list those. And that requires me to find p over q. So my p-value comes from my constant at the end, which was -20, and all of its factors are plus or minus 1, positive or -2, 4, 5, 10, and 20. And then to find the q values, well, q comes from my leading coefficient, which is 1, and we kind of luck out again here. That's only positive or -1. So really, if I take everything in my numerator divided by 1, I'm just left with the values in my numerator. So I'm looking for one of these values to see where it crosses. So my second step will be to graph the function, and we're going to see where it crosses one of those values. So let's look at our calculators, and let's type in, get a new page there, and then we're going to type in x to the 4th plus 4x to the 3rd minus x squared plus 16x minus 20. All right, so we're going to graph that. I'm going to erase these zeros from earlier. And looking at my graph, it looks like I have x-intercepts, or zeros, at +1 and 1, 2, 3, 4, 5, at -5. And if we go back to our list of possible rational roots, I believe each of those make the cut in this case. Can we go back to the, so -1 and 5 were both on there. So we'll say from our graph, we think we're going to test at -1, +1 and -5. So let's start with +1 first. We know to do synthetic division, we're going to use our coefficients from our polynomial, which will be 1, 4, -1, 16, and -20. We were not missing a term in that case. So in order to do synthetic division, we know our first term carries down, and then we multiply by what's in the box, which is a 1. 4 plus 1 is 5. Again, multiply by the box gives us a 5. Add down to get 4. Multiply by the box to get a 4. Add to get 20. And last multiplication is +20 again, which adds to 0, which is good because this is our remainder, which means for sure it is a 0 in this case. To figure out what polynomial we're left with, we count backwards: x to the 0, x to the first, x squared, x to the third. So we know we have factored our x to the fourth, our quartic polynomial, one step. And we right now know that we have one factor of x minus 1 multiplied by 1x to the third plus 5x squared plus 4x plus 20. However, we do want to try to reduce this cubic a little bit more. And so we're going to do synthetic division one more time. And we're going to use that other 0 we saw at -5 to do that. So again, we'll start off with -5 in the box, and we're going to use the coefficients from this cubic to break that down a little bit more. So we'll have 1, 5, 4, 20. And when I bring the 1 down, again, I'll multiply by the box to get a -5, add to get 0, multiply to get 0, add to get 4, multiply to have a -20, and again adds to 0, which is perfect because that again is my remainder. Counting backwards, x to the 0, x to the 1, x to the second, we know that that is going to give us our original factor of x minus 1, our new factor of x plus 5, and what we just found from division of 1x squared plus 0x plus 4. Those are my factors. If I want to see how I could solve this to actually find my roots, well, I would set each factor equal to 0. We know that this first one from setting it equal to 0 will be x equals +1, which we saw in our graph. X plus 5 equal to 0 gives us x equals -5, which we saw in our graph. And to solve our quadratic, again, you could use quadratic formula if you wanted. You could complete the square. I mean, you have lots of options. But because there's only an x squared and a constant, I'll subtract the 4 over. I'll square root each side, and remember to add in a plus or minus. So we'll have x is equal to plus or minus the square root of -4, which is really plus or minus 2i. So again, imaginary, which explains why we only saw 2 places on the graph where it crossed. So altogether, our roots for this quartic polynomial will be 1, -5, 2i, and -2i. Again, it was a degree 4. We should end up with 4 answers, even if some of them are imaginary.
Okay, so let's do this going the other direction. This time we're writing a polynomial function with complex zeros. So if we have a function that has a 0 of 2 plus I, and it also has a 0 of square root of 3, and a 0 of 1, we're going to write the function that has those zeros. So we have to start writing the factors. So if we are going from the zeros to the factors, we might start listing them. If 2 plus I is a 0, then we know that x minus 2 plus I is going to be a factor. But from our complex zero theorem, okay, so we were going to work on this problem, but I think that before we can do this one, or one like it, we actually need to talk about the complex conjugate root theorem. And as I noticed, this one is actually going to end up being a degree 5, so it's going to take us a long time to do that one. So we're going to skip this one, and we're going to talk about the complex conjugate root theorem. And then we'll try an easier problem than that last example. So here's the complex conjugate root theorem. If a plus bi is a root of a polynomial equation with real number coefficients, then a minus bi is also a root. So you remember about complex conjugates. You know, for example, if 3 plus 2i is a complex number, its complex conjugate would be 3 minus 2i. You keep the real parts the same, but you make the imaginary parts opposite of what they were. All right, so if 3 plus 2i is going to be a root, then 3 minus 2i would also have to be a root. Let's take a look at this example. This one's going to be a little easier than that one that we had up before. So in this case, we want the simplest function with zeros, negative 3i and square root of 5. If negative 3i is a 0, let's write down what the factor would be. So if the 0 is negative 3i, then x minus a negative 3i would be a factor. Well, that's the same as saying x plus 3i. And if negative 3i is a 0, think of that as 0 minus 3i, then that's going to be the same as, well, the complex conjugate of that would be 0 plus 3i. So if positive 3i is a 0, that means that x minus 3i is going to be a factor. And we also know that square root of 5 is a 0. So if square root of 5 is a 0, then x minus square root of 5 is a 0. And negative square root of 5 is going to have to be a 0 also. So x minus square root of 5, x plus square root of 5 is going to be another factor. So let's write down what all of our factors are. We're trying to write this function f of x equals, it's going to be fx equals x plus 3i times x minus 3i times x minus square root of 5, and I'm going to run out of room, so let me slide this down here, times x plus square root of 5. So we need to put this in standard form, so we're going to multiply this out. If we multiply these two together first, we can just use FOIL, and we would get first terms as x squared, outer terms is a minus 3ix, inner terms would be a plus 3ix, and the last terms would be a minus 9i squared, because 3i times negative 3i would be a negative 9i squared. Well, I do like that these are going to subtract off, so I'm just going to have x squared minus 9 times I squared. But remember, I squared is really equal to negative 1. So I really have minus 9 times a negative 1. That means I really have x squared plus 9. Well, that's good so far. But we also have to multiply these two together. So let's do that first, and then we'll come back and multiply by the x squared plus 9. So if we do this, maybe I'll do a little box method for this. Even though it's FOIL, let me just do x and negative square root of 5, and x here, and a positive square root of 5. So here I'm going to have x squared. Here I'm going to have minus square root of 5 times x. Here I'm going to have positive square root of 5 times x. And lastly, a negative square root of 5 times a positive square root of 5 is going to be negative square root of 25, which is negative 5. I notice that these are just going to subtract off because it's a positive square root of 5x and a negative square root of 5x. So I'm really just left with x squared minus 5. So I want to multiply that times this one to get my answer. And so if I do FOIL on this to finish this up, first terms would be x to the, nope, not that. First terms would be x to the 4th. Outer terms would be a minus 5x squared. Inner terms would be a positive 9x squared. And my last terms would be a minus 45. So I think that we can combine like terms here and get our function to be f of x equaling x to the 4th plus 4x squared minus 45. So again, this is a degree 4 polynomial function. It will have to have 4 zeros because it's a degree 4, and we know what those 4 zeros are. They're going to be negative 3i, 3i, square root of 5, and negative square root of 5.
Okay, so we have one final example to finish up the video. And again, it's just practicing writing a polynomial in simplest form given the zeros. So we are given our 0 of 2i, which means in factored form, we can think of that as x minus 2i. Again, if you want to think of this as having a 0 out here, then the other 0, because these must travel in a pair, is going to become negative 2i. So its factor will be x plus 2i. And then our last factor is 3. 3 is not imaginary. 3 is not irrational, which means it only will have the factor x minus 3. Again, a big misconception I hear, or I see when I'm grading these, is that I'll see people add in, well, negative 3, but that's not the case. It only has a conjugate pair if it is imaginary or irrational. If it's just a real number, then it's just the number I give you. Okay, so we are going to work on foiling this out. So to find our function, we know in factored form that we have x minus 2, or sorry, x minus 2i multiplied by x plus 2i and x minus 3. Now when you are going to multiply these, really you can take any two you want to multiply first, but whenever you have a conjugate pair, you should always multiply those first so things will cancel out. So if I FOIL this, I'll have x squared minus 2ix. Well, I guess that was actually a plus. Sorry about that. Outside was a plus. Inside is a minus 2ix. And last times last will be minus 4i squared. Again, combining like terms here, I do notice that I have plus positive 2ix and negative 2ix, so those will subtract off and be gone. I'll end up with x squared minus 4i squared. But again, I squared is equivalent to multiplying this by -1. So this factor, or these two factors actually multiply down to x squared plus 4. Now, not forgetting about the other factor I had out front, I now need to multiply that factor by x minus 3. And again, I'll just FOIL. If you want to use the box, you can. But first times first will be x to the third. Outside times outside is minus 3x squared. Inside times inside, positive 4x. And last times at last, negative 12. Again, all of the like terms are already collected in this case. No need to simplify. So our simplest polynomial will be f of x equals x to the third minus 3x squared plus 4x minus 12. Again, we know we have 3 zeros in this case. Although you were only given 2, you knew that imaginary had to have a conjugate pair. All right, so that ends our notes for today.
Thanks for watching.